So now that we know that we're going to be studying observations, I'd first like to focus in on the qualitative style of observations that we can make in a section that I like to call the classification of matter. There are many different ways that we can actually classify matter, but you need to know a little bit more about that matter before you can classify it. I like to use something that looks like this. I call this a decision tree to help me understand the difference between some of the more common ways that we can actually identify or classify our matter. Now, matter is going to be all the way up at the top. It's an extremely general term that just means essentially stuff. It's the stuff that everything is made up of. The first decision that you can go through is to decide whether or not it appears to look the same throughout. They used to call that uniform appearance. And you can choose one of two paths. Heterogeneous means that it does not look the same throughout. So I want you to imagine like a container of muddy water with sticks in it, or a big bag of Skittles, something like that, where you can clearly tell the difference from one part of matter to another part of matter and see that it doesn't look the same. That's what it means to be heterogeneous. Homogeneous, you couldn't tell the difference from one part of it to another. It's going to look the same throughout. So I want you to think of something more like maybe a cup of milk or Gatorade, something like that. The next thing we can decide of is whether or not you know there's more than one thing on the inside of it. In other words, does it have a variable composition? So if you know that it's made of more than one thing, for example, salt and water, salt water, you would call that a homogeneous mixture, or a very special kind of that, which was called a solution, where one thing is dissolved into another. But if you know it's only made of one specific material, you can call it a pure substance. Now, there are two different forms of pure substances, and it depends on whether or not you know there's more than one type of atom on the inside. Now, that can be very, very difficult to tell without actually doing some more chemistry behind it. But sometimes we're provided with a name or a chemical formula that we can actually decide these things. So if you know that it can be separated into more than one type of atom, we call that a compound. Or if it's made of all of the same type of atom, it's called an element. Again, this decision tree really helps me to make those decisions and to classify one from the other. Now, what we're really going to be focusing mostly is the difference between an element and a compound, because that's predominantly what we're going to be using in class. So again, an element is only made of one type of atom. Those atoms can be combined, but they don't have to be. And a compound has to be made of two or more different types of atoms, and they have to be chemically combined. So let's take a look at some examples. So this is a picture where the circles just represent a specific type of atom. As you can see, they all look the same. Would you classify this as an element or a compound? You're right, it's an element. What about this picture? Now you can see there's more than one type of atom here, and they're physically connected. They're bonded. We would call that a compound. And then finally, one more kind of challenge picture. Now this is only made of one type of atom. It's not two or more. However, they are chemically combined, and that's okay. We would still call this an element. Now, there are only very specific elements on the periodic table that will do this, and we'll learn a little bit more about them in the next chapter. We call them the diatomic elements, and it's worth mentioning who they are now. If you actually take their chemical symbols and lay them out, it can spell this really weird name-sounding thing. I call it Brinkelhoff, made of bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. They are so reactive that they only really exist naturally in a diatomic form, or two-atom form. So when we write them, we put these little subscript 2's behind them. And again, you're not really going to be responsible for that this chapter, but next chapter, absolutely. So when I say, don't forget your Brinkelhoff, remember what the Hoff says, and Brinkelhoff. Now, there are other classifications that we can use for matter, and sometimes we can only really figure them out as we're changing that matter. These two different types of changes that we can go through are either physical changes or chemical changes, and they're also pretty simple to understand. Physical changes essentially do not change what the material is made of. It's the same atoms in the same pattern before and after your change. Chemical changes, however, really do change what the substance is made up of. You're going to have atoms that are changing places, maybe even switching in and out of that material. It's not made of the same stuff before and after. Some examples of each. Physical changes. Any phase change, some people would have called this state changes, like melting or evaporating, freezing. Those are all physical changes because you're made of the same stuff both before and after. Chemical changes, however, you're not made of the same stuff before and after. Some examples would be like burning or exploding, rusting, frying. All of those types of changes will actually be different materials at the end than they were in the beginning. Let's double back on these physical changes. There are at least 4 and sometimes now even 5 recognized states of matter. The ones that we are going to be most familiar with are solid, liquid, and gas, and you should know what it's called to go between these states of matter, just like they're shown on the screen. The ones that most people have a hard time with are going between the solid and the gas. If you're just going from solid to gas, it's called sublimation. Gas back to solid, it's called deposition. A good example of that would be dry ice. Dry ice doesn't melt, it sublimes. It actually goes directly from a solid to a gaseous state again. And what I want you to think about during every single one of these changes is, what is this material made of? So here's a picture. You can see ice, water, and steam. What are all 3 of them made of? Well, they're all 3 made of water. So anytime that you're going from ice to liquid water to steam, those are all physical changes, not chemical. I want you to also look about it like this way too. Really the only difference between them is, again, not what they're made of, but how much space is between the particles. So as the material gets hotter, the particles move faster and also have more distance between them. Just to really drive this point home, I have this cute little animation for you. Now I want you to watch this glass of water. This glass of water right now is in the solid state, and you can clearly see the particles are close together and not moving very quickly. But as we add heat, the particles start to move faster. Now we've gone from solid to liquid, and notice the particles on the inside. It's still water molecules. You're not getting the molecules actually breaking down, they're just moving faster and moving apart from each other. This is a physical change. Then if we let this keep going, you'll notice that every once in a while a water molecule is flying out of the cup because it's starting to go into the gaseous phase now. Chemical changes actually are pretty cool. Unfortunately, we are not going to be hopping on the magic school bus and shrinking ourselves down to the size of an atom so we can really see whether or not that they're rearranging. We don't have the equipment for that in class either. So we need some sort of a macroscopic or big scale way of telling when atoms are rearranging at the microscopic or super duper tiny scale. So we have essentially 4 ways that we can tell if a chemical change is occurring. And there are signs that we can look for. One of them, bubbles. Another one, a color change. And we're talking a distinct color change here, as what you can kind of see down on the screen below, where you have something that is slightly light yellow adding with something clear, and all of a sudden this big rusty blob appears in the center of it. Temperature change. Now this is without adding ice and it's without adding like fire or something like that. You add 2 liquids together and you feel the tube and all of a sudden it's burning hot. That's a really good sign that a chemical change is occurring. And then finally, there's this weird one called the formation of a precipitate. And this is usually the one that students have the hardest time visualizing. This is when you add 2 clear liquids together and then suddenly something milky, white, sometimes they can be gloopy, sometimes dark in appearance. There are a variety of different types of precipitates, but that is a pretty good indication that a chemical change is happening. Now, these precipitates themselves are solids that are being formed as 2 liquids meet. Again, a huge sign of a chemical reaction. And just to make sure that you really understand what this looks like, I want you to take a look at this little clip. So I hope you enjoyed that little video clip of the formation of a precipitate and that it helps you when you see these again in the future.